Hello, this is Gregory Maxwell, and in this lesson we will be talking about polynomial functions and their graphs. And PowerPoint credits goes to Shauna Hader, who has created the PowerPoint on which most of this video is based. So let's get into it. Polynomial functions. A polynomial function is a function of the form f of x equal to this form here, a number times x to the n plus another number times x to the n minus 1, and so on all the way down to just a number. These are the numbers here, a subscript n minus 1, and so on. Those are called coefficients. Those represent real numbers. Those are the type of polynomials we'll be dealing with in this course. So polynomials with real number coefficients and the exponents of the variable must be non-negative integers. They must be whole numbers. In the case of a constant, that would represent an x to the power 0. So the x cannot be under a radical or in the denominator of an expression. Now, remember, of course, that the integers are positive or negative whole numbers, not decimals or fractions. Non-negative integers, therefore, are the positive versions along with 0. And the degree of a term of a polynomial is the power to which the exponent to which the variable is raised. In this case, we're dealing with a polynomial function in one variable, so we're only looking at one input. And in this case, we're treating the input as x. So whatever power or exponent x is raised to, that is the degree of that term. When we write the polynomial in standard form, we write from highest power of x down to the lowest, from highest degree down to the lowest. And the degree of the polynomial is the highest power, the highest degree of the x's. So if you look at all the x terms and write them in standard form, the x with the highest power, that power is the degree, and that term is called the leading term, and the coefficient of that term is called the leading coefficient. So in this form, a subscript n is the leading coefficient, and this whole term a n x to the n is the leading term. Now let's do a quick example here. Let's state whether these are polynomials and what the degree is. In this case, the degree, this is a polynomial because the coefficient of x are all real numbers and the degrees are all non-negative integers. And the highest degree here is 4, so the degree of this polynomial is 4. The leading term is 2x to the 4 and the leading coefficient is 2. In this case, this is x to the g of x equal to 2. That may not look like a polynomial, but it actually is, because we can think of it as 2 times x to the 0, in which case the degree would be 0. And the constant, this is a constant, so the leading coefficient is actually just a constant itself, 2. In this case, this function is not a polynomial because the x is under a radical, which means it has a degree akin to x to the half. You cannot have an exponent that's to the half for a polynomial function. So this is not a polynomial function. Neither is this capital F of x equal to 3 over x plus x squared a polynomial function, because the variable is in the denominator, so that is effectively similar to the exponent being a negative, and we're not allowed to have negative exponents for the variables for a polynomial function. An additional characteristic of polynomial functions is this: their graphs are what we call smooth and continuous. That means the graphs have no sharp corners or cusps. They are smooth, and there are also no breaks. So this little graph here is like a polynomial, but this graph I just drew is not a polynomial because it has sharp corners here, or cusps. It has a break or a gap, and also there's a hole in the graph. Those disqualify this graph of being the graph of a polynomial. Now let's talk a little bit about some basic graphs of the roots, the parent graphs for polynomial functions. The first one we're looking at is the graph of x to the n, where n is an even number, an even integer. In this case, a positive even integer. So we're talking about graphs like x squared, x to the 4, x to the 6, x to the 10, x to the 28. And what we notice is that all of these numbers pass to the point -1, 1, and 1, 1, because when you raise -1 to any power, you get 1. When you raise 1 to any power, you get 1. When you raise -1 to any even power, you get 1. If you notice, this is also an even function because the graph does the same on the left side as on the right side of the y-axis. It has y-axis symmetry. That, of course, makes sense. If you raise any real number to an even exponent, you will get the same number of answer whether you raise a positive or a negative to an even exponent. As you can also see, the graph is flatter between -1 and 1 and steeper before -1 and after 1. That is because of our property of real numbers, such that if you raise a number that's smaller than 1 to a power bigger than 1, like 2 or 4 or 8, the result you get is a smaller number. For example, if I raise 1/3 to the power 2, I will get 1/9 because it's 1/3 times 1/3. And 1/9 is smaller than 1/3. So as the exponent gets bigger, the graph gets flatter because you're raising it to a higher and higher power, so you get smaller and smaller numbers. However, that's only occurs between -1 and 1. After 1, when you raise a number that's bigger than 1 to a power bigger than 1, like to the 2 or to the 3 or to the 5 or to the 8, you get a larger number. So for example, 1.5 squared is going to be 2.25. 1.5 to the 4 is going to be 6.25. The number gets bigger as you raise it to a power bigger and bigger power. So that means the graph gets flatter between -1 and 1 and steeper on the outskirts of 1. The end behavior is interesting. In this case, the graph is doing the same thing at both ends. So as you go to the left, the graph goes upward, and as you go to the right, the graph goes upward. Mathematically, we'll say as x approaches -infinity, y approaches infinity. That is, as x goes to the left, that's what we mean by x approaching -infinity. This arrow means approaches. So as x approaches -infinity, y approaches positive infinity. Or in layman's terms, as x goes more and more to the left, y goes higher and higher. X values go left to right, y values go up down. On the right side, we see that as x goes to the right, the graph goes upward. So we say as x approaches positive infinity, y approaches positive infinity. Now let's talk about what the graph of f of x equal to x to the n, where n is an odd number, looks like. When n is an odd integer, the graph is rising on the right side and falling on the left side. The graph is still flat between -1 and 1 for the same reason that it was before, and the graph is also getting steeper to the right of 1 and to the left of -1. But negative inputs give you negative answers, and positive inputs give you positive answers. So the graph is doing different things on the left side as on the right side. So the end behaviors are different. In this case, as x approaches -infinity, y approaches -infinity. But as x approaches positive infinity, y approaches positive infinity. So the end behaviors are different. Now this brings us to a quick little example of a transformation here. We can do a transformation of the graph of x to the 4. If you recall, x to the 4 looks like the x squared graph. So we have this blue graph, this red graph here is x to the 4. So what will happen if we take that graph and multiply -1 and add 2? Of course, multiply by -1 means we're reflecting it about the y-axis and the x-axis, sorry. And then we're going to add 2, so we're going to shift the graph upward 2 units. So it was a graph that opened upward, then we've reflected over the x-axis and then shifted upward 2 units. So there we have it. That's the graph of f of x equal to -x to the 4 plus 2. Now let's talk about what happens with the end behavior of a general polynomial, because the graphs won't all look this simple. So let's talk about those. The two big things that will give us end behavior information are the degree and the sign of the leading coefficient. In other words, the leading term will tell us that. Let's take a look at a graph where this graph has an even degree and a positive leading coefficient. That means the graph is going to be rising at both ends, because eventually, as x gets bigger and bigger and you raise it to an even degree, you're going to get a positive answer. So as you go to the left or as you go to the right, the graph is positive. And since you're multiplying the coefficient, a positive coefficient, the graph will remain opening upward, basically. So the end behavior, the graph rises on the left and also rises on the right hand side. So as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches positive infinity. The graph rises at the ends when the leading coefficient is positive and the degree is even. Now, if the degree is even and the leading coefficient is negative, what that does is effectively flip the graph upside down. So the end behaviors is going to be negative infinity for the y values as x goes to the left or as x goes to the right. The end behaviors will be the same again because the degree is even. But as x goes to negative infinity, y goes to negative infinity, and as x goes to positive infinity, y goes to negative infinity. The graph could turn a number of times in between, but at the ends, the behaviors are the same. As x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Let me just quickly correct that slight error on my part here, so that we can have that in our notes. Now, there we go. Next, in this case, when we have an odd degree polynomial, the graph trends in one direction. It either trends upward from left to right or downward from left to right. If the degree is odd, the graph is going to have different behaviors at the end. If the coefficient is a positive coefficient, the graph trends upward. So it starts low and ends high. As x on the left side it falls, and on the right side it rises. And of course it may do turns in between. As x approaches negative infinity, then y approaches negative infinity. That means as you go more to the left, the graph goes downward. And as x approaches positive infinity, the y approaches positive infinity. As you go more to the right, the graph rises. On the other hand, if you have a graph where the coefficient is negative but the degree is odd, then the graph trends downward from upper left to the bottom right. So the left-hand side the graph rises, on the right-hand side the graph falls. So, and of course it turns in between. As x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y approaches negative infinity. So those are the behaviors of this graph. And here's a quick little summary that is taken from the book Pre-Calculus 5th edition by Plitzer. This is found in section 2.3. A nice summary of what the end behavior does for when you have a polynomial. They call it the leading coefficient test because this information comes from the leading coefficient. Now let's move on to what happens to the graph additionally. The degree of the polynomial also tells us something about how many possible turns it can have. If the polynomial has n minus 1, if a polynomial has a degree n, it will turn at most n minus 1 times. That doesn't mean it has to turn that number of times. It means it cannot turn more than that number of times. So if the degree is 5, the polynomial will turn no more than 4 times. If the degree is 8, the polynomial will turn no more than 7 times. If the degree is 1, the polynomial will turn 0 times. And if you recall, a polynomial of degree 1 is a linear function, so it's a straight line, and straight lines don't turn. So let's take a look at this graph here. F of x equal to x to the 4 minus 3x cubed minus 15x squared plus 19x plus 30. Since the degree is even and the coefficient of x to the 4 is 1, the leading coefficient 1, then of course the end behavior is rising at both ends. As x approaches positive or negative infinity, the graph approaches positive infinity. Now, as you can see that since the degree is 4, the graph will turn at most 3 times. So let's see what is probably going on in between. So to figure this out, what we're going to do is take this function and we're going to factor it. But let's find the y-intercept. To find the y-intercept, you plug in 0 for x, and we see the graph will cross the y-axis at 30. X equals 0, y equals 30. But to find the x-intercepts, it's a little harder. In this case, I have factored the function. We factored the function so that you see what it could be written in totally factored form. Then we've set that equal to 0 so that we can find the x-intercepts. That means using the zero product property, we set each factor equal to 0 and solve for x, and we get x equal to -3, -1, 2, and 5. We can then plot those points on the graph. And once we plot those points on the graph, we can then try to draw a smooth curve through those points, and we get something that looks like this. Not quite, it goes through -3, -1, 2, and 5, and across the y-axis at 30. So that's the general graph there. That was computer generated. Let's look a little more at that concept of where the graph crosses or touches the x-axis. Those points are called roots of the polynomial, and since those places the y-coordinate is 0 when you plug those x values into the function, they're also called the zeros of the polynomial. So this function is in factored form, which makes it easy for us to find the zeros of the polynomial. In this case, one zero is 1, one of them is -2, and the other one is 3. But if you look at this factored form here, this x minus 1 is there 3 times. So it represents x minus 1 times x minus 1 times x minus 1. So this 0 is repeated 3 times. It's there 3 times. We call that the multiplicity of the 0. The multiplicity of the 0. This factor is x minus 1 to the 3. That means the multiplicity of this 0 is 3. This factor is x plus 2 squared, which means this factor is there twice, so the multiplicity of the 0, -2, is 2. And this factor is only there once, so its multiplicity is 1. The multiplicity gives us some detail about what the graph does at those x-intercepts. So let's take a look at what the graph will do at those x-intercepts. We're going to use a different example here. We're using f of x equal to negative parentheses x minus 1 times parentheses x plus 2 squared. When the multiplicity is even, the graph is going to touch the x-axis. It's going to kind of bounce off the x-axis. And when the multiplicity is odd, the graph is going to cross the x-axis. It's going to go through the x-axis. The bigger the multiplicity, the longer the graph links around that intercept before moving on. Kind of gets a little flat. So let's take a look at this example here. We know the end behavior. We have x minus 1 times x plus 2 times x plus 2. So if we were to FOIL this, we'll have a negative x cubed graph because we'll be multiplying -1 times x times x times x. So the leading coefficient is -1 and the degree is 3. So this graph is starting high, ending low. It rises on the left and falls on the right hand side. So the end behavior is as x approaches -infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches -infinity. We can also see that this graph will have at most 2 turns since the degree is 3. Now, we also see that it has the y-intercept is 4 because if you plug in 0 for x and work it out, you will get 4. And then the x-intercepts, we just set f of x equal to 0 and solve for x, and we'll see that those zeros are 1 and -2. 1 has a multiplicity of 1, which means the graph will cross the x-axis at 1, and -2 has a multiplicity of 2, so the graph will touch the x-axis at 2. The next thing we can do is we can draw a graph starting high, coming down to -2, bouncing on -2, going up to a little turning and coming through the point 0, 4, and then cutting at 1. So something like what we just saw right there. And that we have is the graph. So here are a few steps. Again, remember the multiplicity is 1. At 1 is 1, and the multiplicity at -2 is 2. And then here we have a quick little sketch steps for sketching a graph. We determine the left and right end behavior by looking at the leading term. We identify the maximum number of turns as a guide. We identify the y-intercept. We find the x-intercept by plugging in 0 for y and solving for x. We determine the multiplicity of each 0, which are where the graph cross the y-intercept, and then we plot a few extra points to help us to identify some reference points, and then we use a smooth curve to join those points. Also, from the book by Blitzer Pre-Calculus, there are some steps given as well. I have included those in this PowerPoint, in this video presentation, and they also talk about possible symmetry, whether it has y-axis symmetry or origin symmetry, but that should come up as we continue. Now let's take a quick example here. Let's graph f of x equal to x squared times x minus 3 times x plus 4. Let's see what the end behavior is. If we multiply out this function, we'll get an x squared times an x. That will be our leading term, so we'll get positive x to the 4, positive 1x to the 4, which tells us that the ends are behaving the same since the degree is even, and since the degree is positive, the graph is rising. Since the coefficient is positive, the graph is rising at the ends. So the end behaviors are as x approaches positive or negative infinity, y approaches positive infinity. The maximum number of terms we expect here would be 3, since the degree of the polynomial is 4. So it will probably look something like this, opening upward and turning 3 times, sorry. Now let's keep going here. We now need to find out what the y-intercept is. We simply plug in 0 for x, and as you see, when we plug in 0 for x, we get y equal to 0. So the y-intercept is the origin, the point 0, 0. Now let's find out some x-intercepts. We take the function, it's already factored, we set that equal to 0. When we solve for x, we get 3 values. X squared equals 0, x minus 3 equals 0, and x plus 4 equals 0, meaning x equals 0, 3, or negative 4. We plot them in the right order on the graph, and we see that their multiplicities are, the multiplicity of 0 is 2, which means the graph will touch the x-axis at that point, and then the multiplicity of at 3 and at negative 4 will be 1, so the graph will cross at those places. So as we can see, if we draw the graph, it goes through negative 4, turns, goes up to 0, touches at 0, goes down, turns and comes back up and crosses at 3. So then we could plot some additional points and draw our curve, and then here's what the graph looks like when we draw it on a graphing platform. We see here that it's similar to what we have, although their turning points are different, because we didn't find the actual places where the graph turned. We just knew that it turned between those points. So last little point from the polynomial here, a quick example here. What if we're given the zeros of a polynomial and the degree? Could we find the original polynomial? Well, we could find a polynomial with those descriptions. The zeros here are negative 1, 2, and 3. So the polynomial would have to have factors x minus negative 1, x minus 2, and x minus 3. The degree is 3, so those are the 3 factors, no other factors. So we see x minus negative 1 is x plus 1, x minus 2 is there, and x minus 3. If they want this polynomial in standard form, we distribute by foiling these first two and then multiplying the other factor to that result, and we would end up with f of x equal to x cubed minus 4x squared plus x plus 3. And now we'll go on to some examples. Now in this case, let's take a look at this example here. The question says for numbers 15 to 18, the leading coefficient test, use the leading coefficient test to determine the end behavior, and then use that to identify which polynomial is which. So in this case, we see here that this graph has end behavior. The graph goes downward at the ends because the degree is even and the coefficient is negative. So the end behaviors are the same, but the graph opens downward. So we have a graph that looks something like that. It should have at most 3 turns because the degree is 4. Number 16, the graph has an odd degree, so it does opposite at the ends. The coefficient is positive, so it trends upward generally from left to right. So it starts low and then probably turns a couple of times and then ends high. So that's what the graph should generally look like. In this case, this is a degree 2 polynomial, so it has one turn only. Its coefficient is 1, so it opens upward, and so it will just turn once like that. And then with this graph, the coefficient is negative, but the degree is odd, so the graph starts high and turns a couple of times and ends low. And then, as you can see here from these descriptors, the first graph, graph A, matches up with number 17, which is f of x is equal to x minus 3 squared. Graph B seems to match up with number 15, so that's a graph of f of x equals to negative x to the 4 plus x squared. Graph C matches up with number 16. F of x equal to x cubed minus 4x squared. And of course, graph D matches up with number 18. F of x equals to negative x cubed minus x squared plus 5x minus 3. And of course, you could also look at other properties of the graph, such as the y-intercept is negative because the graph crosses, in this case, 0 in this case, 0 in this case, and positive in this case, as you can tell. So there we have that. Let's do a few more examples here. In this case, we're going to find the zeros of these polynomial functions, and then we're going to state the multiplicity of those zeros and whether the graph crosses or touches. If the function is already factored, the zeros are easy to tell, because all we do is take each factor and set it equal to 0. And then that will give us the zeros. So we take our factors here, and the multiplicities won't change our results. So we still have the same factors with the given the multiplicity. So we have two factors here, two zeros here. So I'm going to do a little table thing here. Let me just type this little section up so that we can see what's going to be put right here. So I'm going to put a little box for my zeros, and then multiplicity, and then behavior. And then what we'll do is we will do a little sketch to see a little grid here to see what's going to be the behavior. In this case, we only have two zeros, so we have that there. So if we take a look at this, the zeros, I'm going to put them from least to greatest, are -5 and -2. The multiplicity of -5 is 1 because its exponent is 1. The multiplicity of -2 is 2 because its exponent is 2. So what does the graph do at -5? The graph crosses the x-axis at -5, and at -2 the graph touches the x-axis. And there you have it. Now I recommend that you try the other questions that I did, so that we can you can see the similar approach here. All right, let's try number 28. So in number 28, we can tell right away that the we still only have two zeros here. One of them is negative 1/2, and the other one is positive 4. We get by setting the factors equal to 0. The exponent of x plus half is 1, so that multiplicity is 1, and the multiplicity for 4 is 3, which means the graph crosses the x-axis at both places. But when it crosses at 4, it lingers a bit before it moves on. At 4, it's going to look something like this. You have our x-axis there, and at 4, the graph is probably going to do something to the effect of linger around before it moves on. And at 3, the graph will just cross through at 3, at half, negative half, like that. So it's an even degree polynomial, so it will open downward generally since the coefficient of x squared is negative. Let's move on to the next example. In this case, it's not factored, so we need to factor this polynomial first. So what we're going to do is factor the polynomial. F of x is equal to, the common factor here is x. So we factor out x, and we have x squared plus 4x plus 4. I continue factoring that. I get f of x equal to x times x plus 2 times x plus 2. And that gives me x times x plus 2 squared. So now we have the function is f of x is equal to x times x plus 2 squared. And then, as you can see now, the multiplicity the polynomial has two zeros, and we can deal with those multiplicities again. Let's quickly do this here. All right, so the first 0 is -2, and the other one is 0 in order from left to right. -2 has a multiplicity of 2 because that's its exponent, but 0 has a multiplicity of 1, so the graph will touch the x-axis at -2, and it will cross the x-axis at 0. Let's take a look at this other question here. In this case, there's no common factor, and so it's not easy to factor as this one. However, we recognize that we could possibly try factoring by grouping. So we're going to try that. So in this case, f of x is equal to, common factor for this pair is x squared, and then x plus 5 is what's left over. And in this pair the common factor is -9, and then x plus 5 is left over. So that gives us something nice to work with. F of x is equal to x plus 5 times x squared minus 9. Now x squared minus 9 is a difference of squares, so we can factor that some more to be x plus 5 times x minus 3 times x plus 3. I'm going to write this out just the other way around, just a little bit. Same deal, same deal. And it's important that you remember to factor this stuff completely. Factor completely, because you want to find all possible linear factors. So now we know our linear factors. We have 3 of them, namely -5, -3, and +3. So we can then identify our end behaviors. If we look at we can determine our behavior of our intercepts, or x-intercepts. We have one at -5, one at -3, and one at 3. All of these have multiplicity 1 because the factors don't have any exponents other than 1. So the graph is going to cross at each of these zeros. And there you have it. Now, let's go on to a few more challenging questions. These next examples involve quite a bit of thinking here. It says determine the end behavior, find the x and y intercepts, the x-intercepts, find the y-intercepts, determine if the graph has y-axis or x-axis symmetry or origin symmetry, and then plot a few more points. Now, in this case, this graph has neither x or y-axis symmetry because it has a mixture of odd and even functions. And if you recall, if you add an even function to an odd function, you get neither. So this function has neither origin nor y-axis symmetry. You see that the leading term here is x cubed, which means the end behavior starts low, ends high, and it probably turns at most twice. The graph has an odd degree, so it has different opposite end behavior, and the leading coefficient is positive, so it starts low, ends high. So we can write the end behavior very easily here as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. So that's very simple there. Then let's find our intercepts. I am going to factor the function. So we're going to do f of x, going to factor it by grouping. So we have x squared, and then x plus 1, and then minus 4, and then x plus 1. Turns out grouping works. So we end up with x squared, the x plus 1, times x squared minus 4, which factors further to be x plus 1 times x plus 2 times x minus 2. And so we can then say our x-intercepts they occur at the points -2, 0, -1, 0, and 1, 0. And the graph is going to cross at each of those places because when factored, all the factors are linear factors. There's no exponent other than 1 for each factor. So there we have that. Now, for part D, the y-intercept is pretty simple. Oh, we already said that for part C, the y-intercept is pretty simple. F of 0 is simply equal to 0 cubed plus 0 squared minus 4 times 0 minus 4. So the y-intercept is equal to -4. So the y-intercept is at coordinates 0, -4. We already said that there is no symmetry. So f of -x does not give you the same function, nor does it give you the negative of the original function. It just does not give you the same thing at all. So therefore, the function is not equal to f of -x, is not equal to f of x, and it's not equal to the negative of f of x. So this function has neither y-axis nor origin symmetry. It's neither odd nor even. Neither odd function nor even function. The fact that the polynomial has an even degree does not make it an even function. Then I'm not going to do and sketch any plot any points. I'm just going to do a general sketch of the graph. So we know that the graph crosses the y-axis at -4. And we know that it has x-intercepts at -2, -1, and 2. So we know that the graph starts low and ends high. So we have a graph that looks something like this. Cuts through, and I'm not sure where the turn occurs. So graph is not exactly drawn to scale, but you get the idea of what I'm trying to get at here. So -2, -1, 1 crosses at -4. And this is a rough sketch of what the graph looks like. Let's move on to the next example. F of x equal to x to the 4 minus 6x cubed plus 9x squared. So with this one, we're going to have to do a little factoring again. The leading coefficient is x to the 4 in this. The leading term, sorry, is x to the 4. So we know that the graph is going to open upward, and it's probably going to have at most 3 turns. At most, it may have only 1. We know it must turn at least once because it's ending where it started, so it must turn somewhere. And so our end behavior then is as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches positive infinity. Does the same at both ends. To find the x-intercept, we're going to do a little factoring. We see that there's a common factor of x squared, and then we have x squared minus 6x plus 9. Further factoring of that, we'll see it will give us x squared times x minus 3 squared. So when we do that now, we'll see that we have 2 factors. So our x-intercepts are going to be at 0, 0, which is the origin, and at 3, 0. And then at 0, 0, the graph is going to touch the x-axis, and at 3, 0, it's going to also touch the x-axis because the multiplicities are even numbers. Y-intercept is also pretty easy. F of 0 is equal to 0 because all the terms have x's in them, and so we'll just be adding 0 plus 0. So we end up with the origin as a y-intercept, which we saw right here. Now, this graph again does not have x-axis or y-axis or origin symmetry, because when I do f of negative x and I replace all my x's with negative x, I get x to the 4 plus 6x cubed plus 9x squared. And that is neither the original function nor is it the negative of the original function. So this function is also neither odd nor even. And then we can do a rough sketch of the graph. The intercepts are at 0 and 3. So we can say the graph does something like this. It bounces at 0, goes up, turns, comes back around, and bounces at 3, and goes about its business. So it's a rough sketch. We don't know exactly what's going on those points, but you can plot additional points to see what those values would be. Here's another example. F of x equal to negative 2x to the 4 plus 2x cubed. So in this case, the end behavior, the leading term is negative 2x to the 4. So we know that the graph is going to open downward and it's going to have at most 3 turns. So the end behavior as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches negative infinity. Same end behavior at the ends because it's an even degree polynomial. So for part B now, we're going to do some factoring. F of x is equal to negative 2x cubed with x minus 1 inside the parentheses. then we'll see then that the zeros of this polynomial, are, are at 0 and 1. And in this case, the multiplicity here is 3, so it crosses there, but it's going to linger a bit before we move on. And at 1, it also crosses because that multiplicity is 1. The y-intercept is f of 0, which we can see is 0. So the graph crosses through the origin. There's also still no symmetry here because, again, even plus odd gives you neither. So f of negative x is negative 2x to the 4 minus 2x cubed, and that is neither f of x nor is it the negative of f of x. So the function is neither odd nor even. And then let's do a little quick sketch of the graph here. So as always, it's not going to be drawn to scale, just give a generalized idea. We know that the graph is going to cross at 0, 0, and it's going to cross at 1. Now when it crosses at 0, 0, it starts low. And then when it gets to 0, 0, it's going to do a little lingering before it moves on. That's because the multiplicity is bigger than 1, so it lingers a bit before it moves on. So that's what we were talking about here. Let's move on to our next example. Our next example is f of x equal to negative 2 times x minus 4 squared times x squared minus 25. Now this looks like it's already factored out already, but not quite. In reality, if we factor it out properly, you'll get negative 2 times x minus 4 squared times, this is a difference of squares, x minus 5 times x plus 5. Now that is factored out. And now we can identify the leading term. The leading term is x, negative 2 times x from here, times x squared. So that's negative 2x to the 4. So as again, we see the graph will open downward generally, and it has at most 3 turns. So let's talk about the end behavior then. The end behavior as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y still approaches negative infinity. Then let's see what are our x-intercepts. As we can see from the factored version here, we have our x-intercepts are positive 4, negative 5, and positive 5. And the multiplicity at negative 5 and positive 5 are both 1, so the graph is going to cross at those places, but the multiplicity at 4 is 2, so the graph is going to touch at that place. And of course, f of 0 is simply negative 2 times 0 minus 4 squared times 0 squared minus 25. That looks pretty big. That looks like it's about quite a large number. 16 times 25 times negative 2. 16 times 25 is 200. So we're looking at negative 400 here. So let's take a look at what the graph will look like. Oh, this is negative 400. 0, negative 400. Let me just check something quickly back here. So symmetry, let's take a look at symmetry. F of negative x is equal to negative 2 times x plus 4 squared, because when you have negative x minus 4 squared, it's the same as the square of negative of x plus 4. So that's that. And then negative x squared is just x squared minus 25. This is neither the original function nor is it the negative of the original function. So there's neither odd nor even again. And now for our little rough sketch of the graph. So this graph is going to have a somewhat weird look to it because the axes are so wide. So let's see if we can make it look as proper as we can. The graph will cross the x-axis at -5 and at 4 and at 5. So the graph starts low, cuts through -5, then it will come down back to let me just check something here. I think I made an error. Okay, there we go. -4 squared times -25 is -4 squared times -25. Okay, so I made an error. That was supposed to be a positive 400. So my error was when I plug in 0 minus 4, that's -4 squared is 16. 16 times -25 is -4, is -200 times another -2 is 400. So I'm going to make my little adjustments to my graph down here. And we still have the same x-intercepts, just that my y-intercept was off. So we're going to cross at -5, we're going to touch at 4, and then we're going to cross at 5. So it's not drawn to scale. We start low, and we go up, we cross, we touch, turn, and go along again. So the graph looks essentially like this. It's supposed to touch at 4, but cross at -5 and at 5. And this point here is the point 400, which may not be a turning point. We don't know what's going on there, but this is the rough sketch of the graph. And finally, well, not finally, but we have another couple examples to do after this one, but finally one in this order. I'm going to leave you to try this one on your own and see if you can figure it out. And then I'm going to move on to the next examples here. Construct a polynomial function f with the given function characteristics. Zeros, -3, 1, 4, and the degree is 3. Now, if the degree is 3, then you can have at most 3 zeros. So we know that f of x is equal to some number, let's call that a, times x minus -3 times x minus 1 times x minus 4. We don't know what the leading coefficient is as yet, but we do know the zeros, so we know the factors. So we have a times x plus 3 times x minus 1 and times x plus 4. Now we also know that when the y-intercept is 36. So when I plug in 0 for x, I get 36 for y. So I can then say 36 is equal to a times 0 plus 3 times 0 minus 1 times 0 plus 4. When I work that out, I can now figure out what a is. 3 times -1 times 4 is -12. And then multiplied by a. So that means a is equal to -3. So my function f of x is equal to -3 times x plus 3 times x minus 1 times x minus 4. And I won't write that in standard form, but you can always multiply it out to get it in standard form. Another example, similar situation. We know the zeros and the multiplicities, but we don't know the leading coefficients. So we're going to write A for the leading coefficient. We have x minus -5, and that multiplicity is 2. Then x minus 2, that multiplicity is 1. Then x minus 1, that minus 4, that multiplicity is also 1. The degree is 4, so we should have at most 4 zeros, which we have a duplicate here. So we have 2, which is a duplicated, and then 2 more, that's 4. So when I work this out, I get f of x is equal to a times x plus 5 squared times x minus 2 times x minus 4. I also know that this point is on the graph, so when I plug in 3 for x, I get 128 for y. So I can then say 128 is a times 3 plus 5 squared times 3 minus 2 times 3 minus 4. 3 plus 5 squared is 8 squared. 3 minus 2 is 1, and 3 minus 4 is -1. So we're talking about 128 is equal to -64a, which means a is equal to -2. So then the function f of x is equal to -2 times x plus 5 squared times x minus 2 times x minus 4. And that brings us to the end of this example and this lesson for today. Strongly recommend that you practice these exercises, and also, as always, I recommend you use Khan Academy and OpenStax.org or the OpenStax app, OpenStax, for additional practice and additional free open source textbook on OpenStax. Khan Academy has additional videos that will help you with these, as well as practice assignments that you can work on. All the best. Keep practicing, keep working, keep learning.